Hello, my name is Roy Simpson. I'm a professor of mathematics at Cosumnes River College in Sacramento, California. In this video, I continue my conversation about matrices, and specifically, we're going to be talking about properties of multiplication for matrices, which is actually a cause of confusion for many people when they first learn about matrices. So in the previous video, you should have learned about how to add two matrices, or 3 or 4 or 5 or whatever it may be. The properties of addition hold just as they would for scalar addition. We learned that matrices satisfy or have the associative property of addition and commutative property of addition, as well as having a additive identity and an additive inverse. Before we get too far into properties of multiplication, I'm just going to start with a real basic one. I hinted about this last time. I'll write it out as a theorem. So this theorem tells us if A is a matrix, an m by n matrix, and this is one of the rare moments where I actually use what I consider to be not the best notation for matrices, which would be the parenthetical notation, but using it helps us kind of write this theorem. So A is an m by n matrix, and just a single element in that matrix we'll call A sub ij. And K is some scalar. It could actually be an imaginary or a real number. Then K times the matrix A is actually just going to apply K to each element within the matrix. So it's going to be the quantity Ka sub ij, and it's the m by n matrix. And this is easily seen through an example here. So let's just make one up. Example, we're going to go ahead and let A equal, let's just do a 2 by 2 for speed purposes. So 3, -1, 0, and 8. Then let's do a -4 times A is equal to, all we need to do is, according to this theorem, apply that -4 as a multiple on each element within the matrix. So that would be a -12. Let's see, -4. So +4, 0, and -32. All right. So you can see scalar, what we call scalar multiplication, actually acts the way that we would hope. So scalar multiplication is usually not an issue when it comes to deal with matrices. It's matrix multiplication that is an issue. And so the way I've taught this for years is to approach it using a matrix and multiplying that matrix by a column matrix, which I will sometimes slip up and call a vector. They're the same thing. But this is best learned by multiplying a matrix by a column matrix. So let's set that up. Now I'm first going to go through this via example, and then I'm going to not justify, but actually tell you the true definition of it. But it's easier seen through example first. So we're going to let A equal this matrix again, 3, -1, 0, 8, and B be a column matrix, 2, 1. And we want to compute, so let me write that down, compute A times B. Now, for now, I'm just telling you that this product will exist. However, there are some conditions that we'll need to have satisfied later on so that this product exists. But for now, let's just assume this product exists so that I can showcase how this multiplication happens. So the way you can visualize the multiplication, I'm going to go ahead and rewrite 3, -1, 0, and 8. And we're multiplying it against a column matrix, 2, 1. If you can imagine that column matrix, and I'll go ahead and highlight it here, that guy right there, if you can imagine that being lifted, turned on its side, and superimposed on the square matrix. So in other words, imagine the square matrix just sitting here like this, 3 with a -1 and 0 with an 8. And we have this superposition, or superposition is the wrong word in this course, but we're superimposing a 2, 1. We tilted that matrix to its side here, and we're superimposing a 2, 1 on that. And what I'm going to do, just showcase it via kind of wrangling it up, is I'm going to visualize that moving against that first row, and then I'll visualize it moving against the second row. Again, I'm going to visualize this like laying on top of the first row. So if I do that, actually, let's go ahead and visualize that right now. What we're going to do is we're going to take the products of those numbers. So the 2 and the 3, that'll be, I'll write that out, 2 times 3. And we're going to add the product of the next two numbers, the 1 and the negative 1. And we'll do the same thing. Superimpose, let me just wrangle that up again. Superimpose that guy on the row below. In fact, maybe just for visual, I'll put it below it. Okay, and if you do that, again, you'll get the 0 times 2 plus an 8 times a 1. In the end, this product will be 6 minus 1, which is 5, and a 0 plus 8, just an 8. So the visualization, again, is that we're grabbing the column matrix, tilting it on its side, and laying it on top of each row, taking products and adding. Now, I want to point out a few things here. First of all, note that the original matrix A was a 2 by 2, and the column matrix B was a 2 by 1, 2 rows and a 1 column. And notice when I did that multiplication, because we had 2 rows in this column matrix, we laid it on top. The number of rows for this multiplication to be really well defined, the number of rows that you have in that highlighted column matrix there has to be the same as the number of columns in the actual matrix you're multiplying it against. So let's just go ahead and see how this works with a larger example. Let's just make something up here. I'm going to do a 3 by 3. So let's just make a 1, 2, 3, 4, 5, 6, 7, 8, 9. It's actually a terrible matrix, honestly. And what I'm going to do is multiply it by a column matrix. Again, I'm only multiplying by column matrices right now. I'm going to multiply this by a column, but now when we make this up, to make this work out, remember, I'm going to take whatever column this is, and I'm going to lay it on top of that matrix. Well, you see you have 1, 2, 3 columns there, so I had better be multiplying by a column matrix that has 1, 2, 3 rows. So let's go ahead and just say it's a 1, 0, 2. Okay, we multiply by a column matrix 1, 0, 2. Now I'm going to again visualize, and I'll do this in red here. So 1, 2, 3, 4, 5, 6, 7, 8, 9. I'll visualize that column matrix being tilted on its side and superimposed on each of these. So remember, it was a 1, 0, 2. And if you could see that kind of laying on top, grab this guy. You can see in this first case, it'd be a 1 times a 0. I'm sorry, 1 plus a 0 plus 6. In the second row would be a 4 plus a 0 plus 12. In the third row, it would be a 7 plus 0 plus 18. So what's kind of nice about having that 0 is that it zeroes out the entire center column. It makes that center column worthless, and as far as the computation goes. So I'll go ahead and write this out again. It's going to be a 1 times 1 plus 0 times 2 plus 2 times 3, and a 1 times 4 plus 0 times 5 plus 2 times 6, and finally a 1 times 7 plus 0 times 8 plus 2 times 9. And we get a final answer here of 7, 16, and 25. And again, notice we started with a 3 by 3 matrix and multiplied by 3 by 1. Notice that our answer here is a 3 by 1. That has everything to do with these outer dimensions. So scrolling back up, we had this 2 by 2 times a 2 by 1. Our answer, if you look at the outer dimensions, is a 2 by 1, which is exactly what this is. For this multiplication to be valid, though, the number of columns of this matrix here had to match the number of rows of that column vector, or I'm sorry, column matrix. So the number of columns, and I'll highlight this in blue so you can see what I'm talking about, the number of columns has to match the number of rows. So those 2's, to be a well-defined multiplication in matrices, those inner dimensions must match. Let me scroll down and make sure that our next example matched up as well. Notice this inner dimension and this inner dimension match up. There were 3 columns, 3 rows. That means it's a well-defined multiplication in terms of how multiplication is defined for a matrix versus a column vector. I still haven't written down what the definition of matrix multiplication is. I'm just going through some examples, but suppose that instead, let's flip that last example on its side here. So what if I were to look at the column matrix 1, 0, 2 and try to multiply it by the matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, let's drag that up. Now, remember what's supposed to happen is that you're supposed to take that column, tilt it on its side, and match each row, or maybe I should say each resulting column as you tilt it on its side with its respective column in the matrix you're multiplying by. But this matrix you're multiplying by only has 1 column, and I happen to have 3 columns worth of numbers. A 1, you might not be able to see that, a 1, a 4, and a 7. So that will not work out. This multiplication is not well defined. And you can actually see it if I had just written down the dimensions here. This first matrix is a 3 by 1, and the second matrix is a 3 by 3. And notice that the inner dimensions do not match. So since the inner dimensions do not match, this multiplication is not well defined. You can't actually do it. All right, so we've gotten to a point where we can kind of get a good definition going for matrix multiplication. So let's go ahead and write one down. All right, so I've pre-filled a little bit of the definition in here, and I'm only doing it as a matrix times a column matrix. So we let A be the standard matrix that we've been writing down, n by n matrix, indexed as A11, A12, A13, so on and so forth. There are n columns and m rows, and B is just a single column matrix with n rows. Then the product A times B is defined to be. Now, before I actually write it down, let me just again tell you this definition says right now, by definition, these two have to match up. You'll also see that it will only work if those two match up. But by definition, those two have to match up. Okay, so the inner dimensions must match here. Then the product A times B is defined to be the matrix. Now again, imagine, I'm going to just write maybe a little bit above here so I can kind of ghost it in red here. B11. So I'm just taking column matrix B, tilting it on its side, and imagine that I'm laying it on top of each of these terms. Okay, so here I go. I've got that all written out. Hopefully I don't steal any of the black ink there. And imagine it sitting on top of these. So you can see it right now. It's going to be A11 times B11, A12 times B21, A13 times B31, all the way down the line until A1n times BN1. I'm missing the 1, but whatever. Okay, and you do this all the way down the matrix. Every single row gets multiplied by that, and you add up those products. So here we go. Let's go ahead and just do it. Kind of get this all set up. A11 times B, how did I write that? B11 plus A12 times B21 plus dot, 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 all the way down the line to A1n times BN1. That's the first row. The second row, again, A21 times B11 plus A22 times B21 plus all the way down the line plus A2n times BN1. And you continue that multiplication down until you get to AM1 B11 plus AM2, B21 plus so on and so forth, all the way to AMN, BN1. Now, if you look at that matrix, it looks like a large matrix, but it's not. Actually, that first row there is just a sum of things. It's only one element. You just add those up. It's a single element in that first row. Same thing with the second row, all the way down to the nth row. So this matrix has m rows, but it only has a single column. And notice those outer dimensions of the original matrices were m by 1, and that's literally what our answer is going to be, is an m by 1 matrix. So that's the true definition right there. A bit bulky, and that's why I do that tilt the matrix, the column matrix on its side and lay it on top of each row, because it makes it a little bit easier to do them, to discuss, really. So let's do an example or two just to kind of really get this down. So I'm going to make up an example here. So in this example, I'm using a 4x4 matrix. Notice that I'm using elements in here that are actual functions. There's nothing wrong with that. I'm just playing around with different possibilities here. And we know that if we're going to multiply A against another matrix, because A is a 4x4, the other matrix for right now, we're going to only deal with columns. The other matrix has to have 4 rows. So we're going to go ahead and assume that the matrix B, and I'm going to write it a different way for right now. I'm going to write a lowercase b. The only reason why I'm doing that is just to kind of get it in your mind that column matrices are often written as vectors, and we use lowercase notation for vectors with a half arrow, or some people use a full arrow up above. Some people do the full arrow. I don't. I always use a half. So anyway, you can use a capital B as well, because technically it is a column matrix, but I'm going to make a 4x1 matrix here. I'm going to do it like this, 1, 2, 0, 0. Again, I just want to highlight this idea that when you're multiplying, again, 4x1, when you're multiplying two matrices, or in this case, as I'm calling it, a matrix and a vector, but that means the same thing as a matrix and a column matrix. When I'm doing this multiplication, first of all, the inner dimensions must match, and you can see right here, the 4s do match. The outer dimensions tell us what our result will be. It'll be a 4x1 matrix. So let's go ahead and visualize that we are laying the column vector on its side as a 1, 2, 0, 0. And again, until you're really super used to this, I recommend that you write it like that up above. Let me scroll down a little bit. Like you write like what I did in red up above, so that you can visualize laying that on top of your matrix and moving it down and multiplying each row by 1, 2, 0, 0. One thing you should notice, those zeros mean that you don't ever have to count the stuff in the back there, right? That -1, that sign, don't matter. That 0 and that 1 don't matter. The 2 and the e to the x and the 1 and the 1, they don't matter. So here we go. I'll get a result. I'm getting my pen set up. This equals, see, the first row is going to be 3 plus 2e to the x. Second, and plus 0 plus 0. Second row is going to be x plus 2. Third row is going to be 7 plus 1. And then finally, 4 plus 2. Of course, you should clean that up just a little bit. So it's 3 plus 2e to the x, and x plus 2, and finally 8 and 6. Not so bad, right? So again, this is only, by the way, a matrix versus a column matrix. It's not a matrix versus a full matrix. So that's our next discussion. So let's go ahead and write out how that's done. And again, you may have an author or a textbook you're using. Most textbooks give a full kind of, element by element description. I do not. I have a little trick that I've always used since I was a student, and it works out very beautifully. So let's go ahead and take a look at that. So the definition for matrix multiplication, we're going to have two matrices here. A, which is an m by n, and B, which is an n by k. Now, to kind of dovetail onto what we've been talking about, this entire time, if A is an m by n and B is an n by k, this multiplication is well defined because the inner dimensions match. The outer dimensions, which is m by k, will tell us what size of a matrix our result will be. On the other hand, if I were to take B and try to multiply it by A, B is an n by k, A is an m by n, because these two do not match up, because the inner dimensions don't match, the m and the k, let me highlight those. Because the m and the k do not match up, this multiplication is no good. It will not work out. All right, so that's just kind of the first thing before we even get into the definition. I'm going to write a little bit of this. I'm not actually going to need to write too much, but likelihood is your author doesn't have this. I'm going to write A times B is equal to A times, I'm going to use a little trick notation here. Let's say B sub C1, B sub C2, just bear with me, B sub C3, ... all the way to B sub C. Well, let's see, how many columns does B have? It has n rows and k columns, so B sub CK. This will be the first column of B. And therefore, that would be the second. And so on and so forth. Here's the kth column. It's just my fancy way of saying, listen, I'm breaking these into, it's still A times the matrix B, but instead of writing the entire stupid matrix B out, I'm saying, listen, I'll write it as the first column of B, the second column of B, and so on and so forth. This notation actually is very powerful because when I do the multiplication, just going back to our original definition, kind of some of our previous work here, when I multiplied, let's go to one that's kind of clean here. Okay, this example. When I multiplied this matrix times this first column, I just laid this first column across this matrix, took the product and added them up. It became a column, didn't it? So now if there was a second column, I would take the second column, lay it across, and do the same trick, and it'd be our second column of our answer. And that's exactly what's going to happen here. Let me scroll down. So that product can be rewritten kind of easily as a single matrix where this first column is going to be A times B sub C1. The second column will be A times the second column of B. The third column will be A times the third column of B, and so on and so forth down the line. So you get the kth column of B. You'll still keep the number of rows that A had because, well, that always remains the same. You always still have the same number of rows. But the number of columns we have here are K in the end. So the number of rows for A had M rows. So this will be an M row matrix, but it'll have K columns. So it'll be an M by K. And if you look at in the upper right-hand corner, right here, where we highlighted in blue, our answer should be an M by K. This is actually the easiest way, I think, to multiply matrices. So let's see it in action. And you can compare this to what your maybe your author has written down or something like that, and try to kind of go with that heavy-handed method versus this. So let's take a simple example here. We'll do let's say a 2 by 3. So 1, 0, 5, -1, -1, and 3. So that's 2 by 3. I'm going to multiply it by a matrix B, which is a 3 by 3. Let's say 1, 1, 3, 2, 8, -4, -3, 5, and 1. Okay. Which is a 3 by 3. Now, if I were to multiply these two, oh, by the way, this is A here. If I were to multiply these two, the only way it would happen is if I multiplied A times B. Because b times a, the inner dimensions don't work out. But a times b sure does. So that's going to be a times b. Well, let me actually just steal my notation. It'll just be this way. A times the first column of b. That'll be our very first column. And then a times the second column of b. That'll be our second column. And a times our third column of b. That'll be our third column. Remember, A has 2 rows, so this will have 2 rows, and we see we have 3 columns. So this should be a 2 by 3 in the end. Again, when you're multiplying, you match the inner dimensions to see if you can multiply, and the outer dimensions will tell you the dimension of your result, a 2 by 3. So let's see how this works. I'm going to take this first column, the 1, the 2, and the negative 3. I'm going to write this, scroll down a little bit so I can see it, 1, 2, and a negative 3. And I'm going to visualize that being laid on each of these rows, right? And multiplying them will sum the result. I'll write it right there, actually, so just in between so you can see them. So our first column of our answer is going to be, well, let's go ahead and write this out. Let's see, it'll be a 1 plus 0 minus 15. 1 plus 0 minus 15. And then laying that red ink on top of the second row, you get a negative 1 minus 2 and minus 9. That is our first row. Now I'm going to go back through. I'm going to erase that. Hopefully I don't take out too much of my handwriting. There we go. And now I'm going to go to the second column. Let me get my red pen back. Second column here is a 1, 8, and a 5. So again, imagine me taking that 1, 8, 5 and multiplying it by the first row and adding the results. You'll get 1 plus 0 plus 25. The second row, you get a negative 1 minus 8 plus 15. Not too bad, right? That's our second column. So let's go ahead and erase this now. And we go on to the third column. Again, red ink. It's going. Okay, so that's a 3, negative 4, and a 1. Trust me, you get fast at this and you don't have to do this at all. You don't have to lay the stuff on top. You can just see it happen. But here we go. The first row will be a 3 plus 0 plus 5. The second row will be a negative 3, positive 1, and a 3. Now all I need to do, let me erase that red ink, so if I reference this in the future I don't see that. All we need to do is clean that up. So this is going to equal, let's see, 1 minus 15, negative 14. Let's see, that's a negative 3 minus 9 is negative 12. 26. Let's see, 15 minus 9 is a 6. That's an 8. And this is a 1. There you go. And you see it is actually 2 rows and 3 columns. All right. So I think that's the easiest way to do it. You learn first the matrix versus column, and then that's how you do all matrix multiplications from this point forward. I'm going to give you 2 examples. I'm going to do them very quickly because you can always pause this video and kind of play along. I'm going to take the matrix. I'm just going to make things up here. 1, 0, 1, 2, 1, 1, negative 3, 1, 8. And I'll multiply that against something. Well, that's a 3 by 3. So I need this to have 3 rows. And how many ever columns I want. So let's just do 2 columns here. Did I just do one with 3 by 2? No, I didn't. I did the opposite. Okay, good. All right, so let's go ahead and do this. We'll say a 1, 1, 1, and a 2, negative 3, 1. Okay, so I'm just doing this very quickly. I want to make sure the inner dimensions match. That's a 3 by 3. This is a 3 by 2. And here's how quickly it can happen. So again, Lay that across, I'll get 1 plus 0 plus 1, which is 2. Lay that across the second row, I get 2 plus 1 plus 1, which is 4. Lay that across the third row, I get a negative 3 plus 1, which is a negative 2, plus 8 is a 6. And that, I am now done with that column. Now take the next one and lay that 2, negative 3, 1 across. It'll be 2 plus 1, which is 3. 4 minus 6, which is a negative 2, plus 1 is a negative 1. And finally, a negative 6 minus another 3, which is a negative 9, plus 8 is a negative 1. You can check your work. Pause the video, check my work, see if I did that okay. All right, I said 2 more examples, and I'm going to slightly lie to you because I'm going to do a little tricky, good example here. So let's take a matrix, a row matrix, 1, 5, 3, 8. Now that's a 1 by 4. So, and I'll multiply it by a column. No, not a column. Let's multiply it by a regular old matrix here. 1, 0, 0, 1, 2, 2, 1, negative 3. Notice this is a 4 by 2. So this multiplication is well defined because the inner dimensions match. So again, take that first column, imagine laying it on top and multiplying. And what you're going to get here, actually I shouldn't draw that first. I should talk about the dimensions, right? So the inner dimensions match. So our answer will be a 1 by 2 matrix. In other words, 1 row but 2 columns. So I was just beginning to write that out as a big matrix, but that's actually not what it's going to be. It's going to be 1 row, just 2 separate columns. So let's go ahead and take this guy and lay it across. I'll get 1 plus 0 plus 6 plus 8. 1 plus 6 is 7, plus 8 is 15. Now I'm going to go ahead and visualize laying the second column. Oops. All that stuff just happened. Didn't mean to do that. Second column across. All right, here we go. Let's see. That'll be 0 plus 5 plus 6, which is 11, minus 24. This gives me a negative 13. And there you go. There's our answer. Well, that looks awkward. I'm going to change it slightly. There you go. All right. And the very last example, I promise, is this one right here. 1, 0, 0, 0, 1, 0, 0, 0, 1 times, let's see, I need 3 rows because I'm going up against a 3 by 3, right? So I need 3 rows. Let's do a 1, 2, 3, 4, 5, 6. That's a 3 by 2. Our answer will be a 3 by 2. And so let's see, let's do this multiplication. Take that first column, lay it on top. I will only get a 1. Take the first column and lay it on the middle row. I'll only get 3. Take the first column, lay it on the bottom row. I'll only get a 5. Great, the first column's done. Take the second column, lay it on the first row. I'll get the 2. Take the second column, lay it on the second row. I'll get the 4. And take the second column, lay it on the third row. I'll get a 6. Notice it returned the exact matrix we were multiplying by. That guy right there, which I'll call B, is the same thing as this guy called B. Turns out that matrix, with the 1s and the diagonals, that square matrix is called the multiplicative identity. So let's go ahead and write that and we'll be done here. You'll have to forgive my sloppy handwriting here, but the multiplicative identity is defined to be the capital letter I. It's always a square matrix, n by n. It is also one of those that shrinks or grows to fit the situation. But it's a column, or it's a matrix where you have zeros everywhere except for the main diagonal, which only has 1s. That is a multiplicative identity. All right. Oh yeah, since I talked about it in the addition lecture, I should talk about it here. I'll leave it to you to prove it. However, commutativity is not satisfied in matrix multiplication. So remember, with addition, you can commute. A plus B was B plus A. But let me put this in red, and I'll say, warning, A times B is not necessarily B times A. It can be, but it's not necessarily always equal to B times A. So commutativity of multiplication fails. Commutativity fails. Associativity actually is true. So, and that's usually left for a linear algebra course, but it is true that A times B times C, A times the quantity B times C, is equal to A times B times A times B in quantity times C. That is true. So associativity is satisfied. So this is a kind of a number system, if you will, where we have the failure of one of the axioms that we require. There are 10 such axioms in mathematics to create some special number systems, I guess you could say, in mathematics. But with matrix arithmetic, multiplicative commutativity fails. All right, that's it for this. You can now do anything with matrix multiplications, additions, or simple stuff like that for matrices. The next lecture will be on determinants.